Right now, as you're watching this, trillions of invisible particles are passing straight through your body. They are silent, ghostly messengers from the heart of the sun and from colossal stellar explosions, traveling across the universe for billions of years, only to zip through us as if we're not even here. For decades, they were just a phantom in a physicist's equation. So how did we finally prove these cosmic ghosts are real, and what secrets are they telling us? To find out, we have to build a trap for a ghost. Our story starts with a crisis. Back in the early 20th century, physicists were studying radioactive beta decay, and they noticed something was seriously wrong. When an atomic nucleus decayed, the energy of the particles that came out was less than the energy that went in. The law of conservation of energy, one of the absolute pillars of physics, looked like it was being violated. It was a puzzle that had the greatest minds of the day completely stumped. Then, in 1930, the brilliant and bold physicist Wolfgang Pauli proposed what he called a desperate remedy. He suggested that the missing energy was being spirited away by a new, unseen particle. This particle would have no electric charge, a mass so tiny it was almost zero, and it would interact so weakly with other matter that it could pass through just about anything. It was a wild idea. Pauli himself was so unsure about it, he famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." He had proposed a ghost. For years, that's exactly what it was, a ghost in the machine. The particle, which Enrico Fermi later named the neutrino, or little neutral one, was maddeningly elusive. Neutrinos don't feel the electromagnetic force, which is what governs most interactions between particles. They are phantoms that drift through the spaces between atoms like they aren't even there. So, just how ghostly are we talking? Well, a single neutrino could fly through a block of solid lead 1 light-year thick without ever hitting anything. Every single second, trillions of them from our own sun are streaming through the Earth and everything on it. So if they're all around us but refuse to be seen, how do you even start to build a trap for one? The answer isn't to build a better wall, but a bigger, smarter net. A much, much bigger net. To catch a ghost, you have to go somewhere extremely quiet. Scientists have built colossal detectors deep underground, in the ocean, and even in the Antarctic ice, using the entire planet as a shield to filter out the cosmic ray noise that bombards the surface. Go a kilometer beneath a mountain in Japan, and you'll find Superchemio Kondi, a gigantic tank holding 50,000 tons of ultra-pure water, surrounded by over 11,000 golden, light-sensing eyes called photomultiplier tubes. Or travel to the South Pole, home of the IceCube Neutrino Observatory, where thousands of these sensors are embedded in a cubic kilometer of pristine ice. These immense detectors wait, patiently, for a 1 in a trillion event. On the rare occasion a neutrino actually smacks into an atomic nucleus in the water, or ice, it creates a charged particle. This new particle flies off faster than the speed of light in that medium, not faster than light in a vacuum, but faster than it can travel through ice or water. This creates a cone of faint blue light called Cherenkov radiation, which is basically an optical sonic boom. The photomultiplier tubes detect this tiny flash, capturing the ghost's fleeting signature. By analyzing the light, scientists can figure out the neutrino's energy and where it came from, pointing right back to its cosmic source. After decades of work, these incredible ghost traps are finally paying off, opening a brand new window on the universe, neutrino astronomy. When a massive star dies, it collapses and explodes in a supernova. In the first few seconds of that cataclysm, 99% of the star's immense energy is blasted out not as light, but as a torrential flood of neutrinos. These particles escape the star's superdense core instantly, giving us an early warning and an inside look at the engine of the explosion. We've only seen one supernova in neutrinos so far, back in 1987, but today's detectors are linked to an early warning system, ready to alert astronomers across the globe. Neutrinos are also helping us crack one of the biggest mysteries in astrophysics, the origin of high-energy cosmic rays. Because neutrinos have no charge, their paths aren't bent by magnetic fields, they are cosmic straight-shooters. In 2018, IceCube traced a high-energy neutrino back across 4 billion light-years to a blazar, a supermassive black hole spewing out jets of particles. For the first time, we had identified a source for these incredibly powerful cosmic rays. More recently, IceCube has even produced an image of our own Milky Way galaxy using only neutrinos, proving that sources exist within our cosmic home as well. From a desperate remedy to a cornerstone of modern astronomy, The neutrino has totally transformed our view of the cosmos. Each faint flash of light in a detector is a message sent from the universe's most violent and mysterious events. And the quest is really just getting started. Next-generation experiments like Hypercameo in Japan and KM3NET in the Mediterranean Sea will be even bigger and more sensitive. They will hunt for neutrinos from the dawn of time, investigate the difference between matter and antimatter, and maybe even find clues about the nature of dark matter. The ghosts of the universe are finally starting to talk, and they have so much more to tell us. What cosmic mystery do you think neutrinos will solve next? Let us know in the comments below. And if you want to keep exploring the unseen universe with us, make sure to subscribe and hit that bell to stay notified.